Hi guys, welcome to KK Chemistry. Today we are going to discuss lecture number 15 of Inorganic Electronic Spectroscopy. Of course, this is lecture 15 part 1. Okay, here the topic of discussion will be mainly excited state for F2 system, F2 system using pigeonhole diagram. You are familiar with the word pigeonhole, like it is just like groups of keeping pigeon in different boxes with different arrangement. Okay, you can see it over here. Just like pigeon, we can place electron in different microstates, or you can say energy, by keeping their ml, small ml value, means magnetic component of L, and resultant ml value horizontally. So here we will discuss actually f2 system, and you know that f2 system is mainly either 4f or 5f block elements of lanthanide series or actinide series. So the trivalent exchange states of these f block elements are highly stable, or you can say favorable. Okay, in pigeonhole, like we have previously discussed, that we can have ml value for a particular orbital in any subshell, and the resultant ml value comes in the form of ml. Here, now we are going to start term symbols derivation for f2 system. You know that lanthanide elements are having the last electrons to be filled in the F subshell. Here it is a 4F subshell. So praseodymium we have taken over here. The electronic arrangement of praseodymium or xenon 4F2 5D1 6S2. It is the ground state electronic configuration of xenon. Okay, when these two electrons are removed from the S shell, it becomes, and one from the D, it becomes Pr plus 3, means the trivalent excitation state. And you are also aware of the fact that the orbitals are actually denoted by its azimuthal quantum number. For if we have azimuthal quantum number 3, well, by using this formula, ml is equal to 2l plus 1, like here putting the L values 2 into 3 and plus 1, we will get 7 orientation of this F subshell under magnetic field. It will range from plus 3, plus 2, plus 1, 0, minus 1, minus 2, up to minus 3. So we can place these two electrons in these 7 orbitals. Okay, here are these 7 orbitals, a much complex one as compared to the p and d orbitals. So now question might be in your mind how you can, or how many boxes you can form, or how many energy levels are there which are used by these two electrons, or you can say in other words how many transitions are possible for F2 system. We can get it from the number of microstate formula, or you can say number of energy levels. This formula tells us that how many energy levels are possible for these F2 electrons. Here the N represent number of successive electrons like 1, 2, 3, 4 up to 14 for a F subshell. Here we have 2 electrons, so we will just confine our cell up to 2 electrons, where N1 is for first electron, N2 is for the second electron, and L, you know, represent the azimuthal quantum number for a particular subshell, and this one symbol represent a product. So now just we are trying to find out the number of energy levels. Okay, here formula is 2 into 2l plus 1 minus n plus 1 up to n. Okay, we know that L is equal to 3, putting value of L over here. For first electron, minus 1. Here it is also 1, first electron. For the second electron, it will be minus 2. The rest of the formula will remain the same. 2 means second electron. So just by computing, just calculating, using the addition, multiplication, and division, we can get 91 energy levels. So there are 91 possible ways of placing these electrons. Now how you place these electrons? You know that ms or s means resultant spin of both electrons. Here in this case we will be talking about the parallel spin. Okay, in case of parallel spin we will have S1 1 over half plus S2 1 over half. 1 over half and 1 over half, it will give us a 1. By putting the value of S in the spin multiplicity formula, we can get a triplet state, means 3. Okay, 2 into 1 plus 1, it will give us 3. 3 means triplet. So a triplet we can get from a parallel spin, and the ml value here will be calculated by adding the ml1 value of first electron and the ml2 value of the second electron. Means here this one is ml, so if electron are over here it will be ml1, if it is here it will be ml2. So adding both these value, it will give us a plus 5. The rest you can calculate in similar way. Like now placing this electron first in the maximum ml value. Okay, now push the pink counter electron upward, black one horizontally. Just keep on moving until you finish with other possibilities. Okay, so here we have finished with all the possibilities for this particular arrangement. Mean if the electrons are in plus 3 plus 2 ml values, small ml plus 3, small ml plus 2, you can have up to here the arrangement of or you can say placement ways. How many? 1, 2, 3, 4, 5, 6. So here you can use a trick. Here we have how many? 7 boxes. You have 7 boxes for arranging these electrons. Okay, so sorry, my drawing not that much good. Now just shift the other electrons. These two electrons are shifted over here, +2 +1. Now pushing these electrons, the pink electron, in upward movement and as well as horizontally. Just keep on moving till you finish the last one, or you can say till you reach the last box. Here, how many placement ways for this particular set of electrons? 1, 2, 3, 4, 5, 6. Keep on moving. Okay, we have reached up to the final state. From here onward, we cannot move these electrons. Here 6 boxes, here 5 boxes, 4 boxes, 3 boxes, and 2. Okay, if you forgot how to place, how to arrange these electrons, you can just keep in mind the number of boxes for each set of electrons. Okay, now coming toward the singlet. Here ms value is 0. How? One electron is in upward direction, the second one is in downward direction. So adding both values, it will give us 0. Putting this 0 in this formula, 2s plus 1 means 2 and 2 0 plus 1, it will give us a 1. Give us a 1. Okay, here in this case it was a 3. So the ml value again, ml is equal to small ml for this one and small ml for this one. Just add both these values, it will give us a plus 6. Okay, now keep on moving electron in similar fashion as you have done with the triplets series. Keep on moving till you reach the final box, beyond which you cannot place these 2 electrons. Okay, here's the final one. Now again, question might be in your mind, how to determine the term symbols for these particular set of electrons. Well, first the triplet one. We have set 1, set 2, set 3. For the singlet, we have set 1, set 2, like set 4. This one. Set 4 is set 4, set 5 is from singlet state. Here, set 6, and the last one is a set 7, this one. So how many sets we have? We have 7 sets of arrangement, or you can say we have 7 sets. We will be having 7 term symbols. First one, where the maximum ml value is 5. So we will have term for this particular set triplet H, spin multiplicity 3, L is equal to 5. The second one 3, the maximum value is ml3. So we will have plus 3 plus 2 plus 1, 0, minus 1, minus 2. The term symbol will be triplet F. Next one is triplet P3, because here we have maximum plus 1. So plus 1, 0, minus 1. Likewise, you can say in a similar fashion, you can just calculate term symbol for the singlet state. Here we have maximum 6 ml value. So plus 6 means plus 6 plus 5 up to minus 6. So term symbol will be singlet I. Because if L is equal to 6, term will be I. Has P multiplicity is 1, means singlet. Okay, set 5. This one, the maximum ml value is plus 4. So you will have term symbol G, as here is display multiplicity singlet. So it will be singlet G. Again, the set 6 is starting from plus 2 up to minus 2. So for 2, if we have L is equal to 2, term will be D, and it is singlet, so term will be singlet D. The last one is a set 7, this one. So here this one is a set 7, where ml value is 0, so term will be S. It is singlet, so term symbol will be 1S. So over here we have again L is equal to 5, L is equal to 3, maximum L is equal to 1. In singlet we have maximum ml value 6, 4 plus 2 and 0. Okay, so you can calculate the ml value in this fashion. Here it is 1, 1, 1, 1, 1, slight typos mistake, 1, 1, 1, 1. Okay, next. We move the total number of term symbols. In the previous case, we have just partially placed the 2 electrons in various energy levels. For complete pigeonhole diagram, you will have 91 boxes, which is not possible over here. Okay, again, we have 7 set 1. The maximum ml value is 5, term will be H spin multiplicity is 3, so triplet H654. You can calculate J value over here. So by calculating J value, we know the term symbol for set 2 is a F spin multiplicity 3, so triplet F432 will be complete term symbols. For set 3, M is equal to 1, M is a triplet 1, the spin multiplicity is triplet, so term symbol will be triplet P210. Okay, you can also calculate the rest one. Okay, so we have total term symbols over here, and the ground state is triplet H4. According to Hund's rule, term symbols with higher spin multiplicity, higher H value, and lower J value in case if the subshell is less than half filled will be the ground state. Here the ground state is a triplet H4. And this total degeneracy means how many ways are there to place this electron. Of course 99 ways. We have calculated it from the number of microstate formula. We can also calculate it from total degeneracy as well. Okay, for H is equal to 5, multiplicity is triplet, put it in this formula, L is equal to 5 is spin multiplicity, so 33 states are over here in H, 21 in F, 9 in P, 13 in I, 9 in G, 5 in D, 1 and S. Here 1 means that S cannot be splatted into further like MJ value, or you cannot be splatted under magnetic field. It can be splatted into 5 other energy levels. 9 ways of splitting these. Okay, here it is 9 ways. 13 ways are there to just orient or split the I under magnetic field. 21 ways of orienting or splitting the F term symbols under magnetic field. Here are 33 orientation, or you can say splitting ways for the term symbols H. Next lecture will be part 2. Okay, it will be diagonal method for excited state term symbols.